In this video, we're going to learn how to take a root of a complex number. What am I even talking about? You're probably used to things like the square root of 4 is 2 or the square root of 25 is 5. But what if I asked you for the square root of I? What is that even equal to? What if I ask you for the square root of 5 plus 2i? How do I get that? And so what we're going to do is we're going to learn how to actually solve problems like that in this video. Now, before I continue any further, I want to point out something. When we use the square root symbol on real numbers like this, we specifically mean the positive answer you get when you take the square root. So square root of 25 is just positive 5, it's not negative 5. However, if we don't use the symbol and we say the square roots of 25 are positive 5 and negative 5. So there are in fact two square roots to every number. The difference is if we use the specific square root symbol, then we mean just the positive answer. And if we say square roots in general, we mean both the positive and the negative. It's important for us to distinguish between what's being asked on a problem. When we're dealing with complex numbers, we're always going to list out all of the possible answers. So there's going to be 2 square roots of every number. There's going to be 3 cube roots of any number, 5 fifth roots of every number, and so on. You have to list out all of them every time. And it turns out there's a nice formula that tells what they are, as long as you have a number in trigonometric form. So if you're trying to find the nth roots of the trigonometric number RCIS theta, all you have to do is you take the nth root of the real number, and that goes in front, and then you divide the angle by the root that you're taking. So if you're talking about square roots, you divide the angle in half. If you're talking about cube roots, you divide the angle in 3, and so on. And we can just check really quickly here. Let's say we want, square root of RCIS theta. Well, if we square root the front number and we divide the angle by 2 and we want to square that answer, we know from the previous video from De Moivre's theorem, you would square the front number, so square root r squared, and then you would double the angle inside, and the square root of r squared is r, and 2 times theta over 2 is theta, and so we do in fact get back the answer we want, so that's a perfectly good square root. But I just told you that in square roots, we're always going to have 2 different square roots for a number. And here's how we're going to get the second one. The second one is going to be by taking the same modulus, the same magnitude in front. You still divide the angle by n, and then you add on 1/nth of a full circle rotation. So 360 divided by whatever root you're talking about. For this square root example, you keep the square root r in front, so the magnitude is not going to change. You keep the theta over 2 the same, but then you add on, in this case, half, because it's the square root of the full circle rotation, or 360 degrees. And then now let's see what happens when we square this. So De Moivre's theorem kicks in again, square the front, and then multiply the inside by 2. And then when we distribute that, we're going to get 2 times theta over 2 is theta, plus 360 degrees. And that's always going to work because you're multiplying by the power, which is squared, and you divide it by 2 in the first place. If it was cube root, you'd be multiplying by the power 3, but you divided by 3 in the first place is always going to cancel out and give you 360 there. And then we know that because the period is 360 degrees, you might as well not even have that in there, and you still get back to the same number, RCIS theta, because of the fact that cosine and sine are periodic with a period of 360 degrees. And if you had cube roots, you would do this, and then you'd add on double the 1 over n times the full circle, and then triple, and so on. You keep doing that until you can't add any more of them. So it's n minus 1 times that. And each time it's going to work out, again, same because of the period. So you're always going to work out to the original number, RCIS theta. So that's a lot of theory here. Let's do a couple of specific examples and you can see how this works. I do want to point out, once again, that we're going to give you the answer, or we're going to give you the problem in standard form, but you can't do any of the work until you convert to trigonometric form. So we have the negative square root 3 plus I. We want the square roots of that. So we have to first convert this into trigonometric form. So we go square root 3 to the left. We go 1 up for negative square root of 3 plus I. Pythagorean theorem says this is going to be a hypotenuse of 2. And then we need to know what the angle is. And it's, again, the angle from the positive x-axis. So we have to think about what angle would make this happen. Well, based on our knowledge of special right triangles, the reference angle is 30 degrees here. Right? It's a 30, 60, 90, and it's opposite the smallest side. So then that means this angle is 150. So negative square root 3 plus I is the same as 2 CIS 150 degrees. And now if we want to find the square roots of that, so the 2 square roots are, and both of them have the same magnitude. It's the square root of the previous magnitude. So the previous magnitude was 2, square root that. And then we do CIS. And the first one is you take whatever the angle is and you divide by 2. So 150 divided by 2 is 75. And the other one is you take that angle divided by 2 and then you add on 360 degrees divided by how many roots you're finding, in this case 2 of them. And so this is going to be square root 2 CIS 75 plus 180 is 255. And so the 2 square roots we're looking for are square root 2 CIS 75 or square root 2 CIS 255. And if you wanted to, you can convert them back to standard form, but there's really not any need to here. So once we're good with that, let's look at the next example, which is the cube roots of 1 minus I. Once again, we're going to start by converting this into the trigonometric form. So 1 to the right, down 1 on the I part. So we're here at 1 minus I. And we know this is a 45, 45, 90 right triangle. So this is a 45-degree angle here. That means measured from the x-axis, this would be 315 degrees. So we have this here. We can write 1 minus I. Oh, and the hypotenuse, which is the magnitude, square root 2. So square root 2 CIS 315 degrees. Now that is the trigonometric form of the complex number they gave us. If we want to find the cube roots of it, so the cube roots are, the first one is you take the beginning number, square root 2, and then you take the cube root of that number. Now that looks a little weird, and you might have forgotten how to combine different roots here. But the square root of the cube root is going to end up becoming the 6th root. We'll deal with that a little later. And then it's going to be CIS, and it's going to be whatever the original angle was divided by 3. So this is going to be the 6th root of 2 CIS of 105 degrees. That's the first of our cube roots. Then for the other cube roots, they keep the same magnitude. And they start with the same angle, 105, but now they're going to add on 1 part of the full rotation. And since we're doing cube roots, we divide this by 3 here. So we're going to get the 6th root of 2 CIS. 360 over 3 is 120. 120 plus 105 is 225. That's our second cube root of this number. And then our third cube root, again, you keep the same magnitude, 6 root of 2. You keep the same starting angle, 105. But this time, we're going to double the amount of the rotation we're going to have here. So previously, we added 120 degrees. Now we're going to add 240. And we're going to get the 6th root of 2 CIS 345 degrees. And this will be our third cube root. And then that means we're done. If we had talking about fourth roots, we would have had to go to a fourth step and so on. And again, you can choose to convert these to standard form if you prefer, but it's not really necessary. And this is how we find any roots of any complex numbers. Just keep using the same process every single time, and you can find the roots.